Okay, so I'm going to talk about Halogen, which is a UI library that we've been building recently for use in the fun data front end. So what is Halogen? Halogen is a toolkit, or I would describe it as a toolkit for building reactive web apps in PureScript. So it's not the only option for building front-end applications in this kind of reactive style, but it does have a couple of sort of distinguishing approaches later, which I'll go over. And I say toolkit in the sense of we try not to sort of impose. There are a bunch of tools like I'll show signal functions and a particular HTML DOM templating library that come as part of Halogen, and a few other features that I'll go into. But it's possible to kind of switch those out, and you could use the signal function piece with the canvas, for example, or you could use the HTML DOM templating with PureScript signal, which is a different kind of FRP type implementation. So the key ideas, or the key tools that Halogen provides are signal functions, and then a DOM templating library that's built on top of virtual DOM. So let's say the virtual DOM is sort of the principal backend of this DSL. If you're not familiar with virtual DOM, it's sort of like it's an open source JavaScript library which essentially acts as the diffing and patching component of React in a sort of very cut down. It sort of provides just the diffing and patching type functionality that you'd expect from a library like React. So if you're not familiar with React, the idea is that instead of sort of sending large DOM updates, large sort of element updates to the DOM all at once, typically if you press a button, you'll make an ajax request. Some things will change, but changes tend to be localized to one or two locations of the DOM. So if we can diff an entire representation of the DOM and just get those small patches, we can apply the patches quickly rather than having to change the whole screen all at once. So, like I say, virtual DOM is one backend. We also support, there's a string renderer, but theoretically you could support multiple backends like Markdown, or you could sort of render things to the console. There's various ways of interpreting this templating DSL that we have. Like I say, it's used in production, it's used in the Slam Data front end, which I guess is going to be released next week. So if you want to see a large-scale application of these ideas in a real system, then it's open source. That's a great place to look. And it's inspired by a few libraries. There's a library called React Blaze, which is written, I think, for GHC.js, but in Haskell, which combines. It's a wrapper for React which uses the Blaze HTML templating library and these kind of FRP ideas. And also Elm, so if you're familiar with Elm's signal functions are kind of like a variant on that idea. So I'll build up to signal functions by looking at signals. And then there's a library called Thermite, which I worked on, which is in my GitHub repositories. Thermite is a wrapper for React, and the API looks, if you sort of squint enough, it looks a little bit like Halogen. But they're kind of very different in approach. So I'll say when I started PureScript, I kind of had my own kind of use case. I said earlier that I wanted to use it for bits of a TypeScript application where TypeScript kind of wasn't doing enough type checking for me. So I had this use case of kind of, I wanted libraries like underscore, but I wanted sort of more functionality in underscore, and I wanted sort of more types, and I wanted to use things like reactive extensions and give sensible types to things in reactive extensions and use monad and things. And that's kind of like one way PureScript development has gone, and I think there's still kind of like a group of people doing that. And then there's sort of the Haskell way. I think Thermite represents the first way. So like kind of these taking like minimally viable type checking, if you like, and just sort of using the type system but not using it in sort of like extreme ways. And then there's like the Haskell way where we're sort of adopting all these sort of type classes from Haskell, which is kind of like a complementary way of writing PureScript. And two different approaches. I think in a certain sense, like Halogen and Thermite kind of represent those two different approaches quite well. So you'll see in this talk we're kind of going to go down the rabbit hole of Haskell style type class based development. Okay, so I want to motivate the idea of signal functions and why they're useful. It's an abstraction for Halogen. So if you've seen things like Elm or Haskell's reactive library or other FRP implementations, you have this concept of a signal or a behavior. So signals are, so I'm going to have this these conceptual types, and these aren't how the code is actually implemented in Halogen, but it's good to sort of get a handle on what's actually going on, how you can sort of think of these types. So signals are values which change over time. Conceptually, a signal of values of type A is a function from some abstract concept of time to A. So we have, let's say, the mouse position, which is moving over the screen. That's a signal of tuples of x and y coordinates. Or we have the signal of whether a button is currently in the process of being clicked on the DOM. That's a signal of booleans. And you can combine these things in various ways. Okay. So I just gave a couple of examples of signals. There's mouse position. You might describe mouse position as having the type signal of point. Key pressed might be a function from the key that you're interested in listening to a signal which tells you whether it's depressed at the current time. So if you're interested in this kind of approach to FRP in PureScript, then there's a great library called PureScript Signal in Bodil Stocky's GitHub repositories, and that includes, I think, things that look like these two signals and ways to combine them. It looks a lot like Elm. It was inspired by sort of the Elm approach. So we have these simple signals, and then the question becomes, how do we build these up into more interesting signals that actually represent the state of an application? So in PureScript, we try and describe common behavior using common type classes, so that we can reason about those type classes and how they interact with each other, and how we can try and prove things about inhabitants of those type classes by using laws. So we expect signal to be an instance of various type classes. Functor is one of them. So functor says, if I give you a function from something of type A to something of type B, and I give you a signal of type A that is a time-varying value of type A, then every time that value changes, or rather at every time point, I can go and get the value of type A from the signal, apply the function that you gave and get a value of type B, and now I have a signal that varies over time and has values of type B. So we say that signal is a functor, and there's various laws that tell us how we can reason about signals as functors. So as a quick example, let's say we wanted, the type signal is wrong here. This should say signal of number. But let's say I was interested in the mouse position, but I was only interested in the x coordinates of the mouse position on the screen. Then I could use the functor instance. That's this dollar in angle brackets symbol, mapping the extractor for the x property over the mouse position. So let's say that point is represented as a record of x and y coordinates. But I should say, by the way, just stop me with questions if anything isn't clear. So that, like I said, this should say signal of number. That takes a signal of points, which is the mouse position, and gives us a signal of numbers, which is the x coordinate signal.
The syntax thing in PureScript, so underscore dot x, is that like an anonymous function?
That's just syntactic sugar. So if you're familiar with Scala, so I'm not an expert in Scala, but I know it has these underscore essentially it desugared into the function that you have lambda p goes to p dot x, and the underscore determines where the bound variable goes. We don't have the equivalent thing that Scala has, but we do have it for record creation, elimination, and updates. So it just turns out that those are it's irritating enough to write those by hand that we decided to add that syntactic sugar. Okay, so that's functor. The next one is applicative. So if functor says that I can take functions of values of type A to B and lift them up into this signal type constructor. So I take A to B and I get signal A to signal B. That's a function of one argument. Applicative says, well, you can also do it with two arguments. In fact, if you can do it with two arguments, and pure looks a lot like the thing with zero arguments, then you can lift functions of any arity over the signal type constructor. So if I have a function from A to B to C, and I have two signals, a time varying value values of type A and one with values of type B, then every time I can take those two values, the latest ones, run them through this function, and get a value of type C, and that's my value of C at that time. And again, this is captured by the applicative type class. We have laws for reasoning about applicative type class, but you can think of sort of parallel composition. Applicative, you can think of talking about as parallel composition of signal values, so taking the latest values. So that was the example. That example, we just lifted a function of two arguments. More generally, with applicative, we use this operator star in angle brackets, which you might pronounce app. And that allows us to lift functions of arbitrarity, like we were saying before. So let's say we have some application state, or some state that represents our so the state of the outside world varying with time, called input state. Let's say this is like an asteroids game. We're interested in whether we're currently firing the weapon and the direction that the vehicle should head in. Let's say we want to be able to combine various user inputs like keyboard and mouse and get a signal time very value of this input state, so that we can process it and use it to update our application. So this is that same syntactic sugar again, but now for updates. So this is a function which takes two arguments with two underscores. The first one is going to go in the first slot, and the second one is going to go in the second slot. And we're going to map that function over two signals, key pressed, whether the space key is currently depressed will give us a boolean, and the current mouse position I'm going to use as sort of the direction of where the vehicle should be heading. So I lift these two up and I turn this into a signal of input states. Does all make sense? Okay. So another kind of standard combinator that you would expect to see in this type of library, like in FRP library, is something called stateful. You might also have seen it called stepper in Haskell or fold P in Elm, with things curried appropriately. So the idea is that I have I want to create a signal that varies with time and return some state of type S. And I've been given the signal of inputs of type I. So every time, so we're thinking at this point of I as being a discrete signal, so it's going to sort of fire in, it's going to fire in sort of discrete events. Every time an event fires, what I want to do is change the state of some black box that represents my return signal. I start with an initial state here, given by S. Every time I get an input of type I, I'm going to take the S that I already had as my current black box state and run it through this function with the I that I got and get a new state out. And that's going to be this sort of time evolving signal of states that sort of gets updated every time these events of type I come in. So for example, let's say we have some monoid, let's say it was integers under the maximum operation, the maximum binary operation, with negative infinity as the empty value. Then if I have a signal of that monoid, I can combine them as the events come in. I just continually sort of combine the values that came in with the current value and the latest value using the binary operation given by the monoid. So in the case that I described, you're going to have numbers coming in, and the result signal is going to be the maximum value seen so far. So stateful gives this sort of way of creating sort of step functions, signals that look like step functions. Okay, so the other sort of component, I'll get into sort of from signals to signal functions in a second, but the other kind of key component of Halogen is this DOM templating DSL. And again, if you're familiar with things like Blaze HTML or Elm HTML, these things are going to look pretty familiar. So instead of writing HTML in an HTML file, we use just plain old functions to build up a data structure representation of the DOM we want to render. So we can use things like div to create a div. The first array, so we pass two arrays in as arguments. So the first array is going to be an array of attributes that I want to apply to that element. And the second array is going to be an array of child elements that are going to go inside that element. So I'm going to have a div with a h1 and a paragraph inside, and I'm going to apply the class name, the CSS class contained to that. And with the h1, you'll see it has an underscore character. That means that I don't want to provide any attributes to this, this h1. I just want to use the default attributes. But I do want a text element to go inside, and it's going to say hello world. And the same with p, and I messed up again, I should have an underscore on it. But the idea is that instead of sort of creating HTML elements directly, either in a HTML file or using jQuery and pasting them directly into the DOM, we've separated the rendering from the representation of the data. So that means we don't have to sort of update it all at once. We can use things like virtual DOM to diff these things and just generate the minimum amount of work we have to do to put it onto the DOM. Okay, so given that DSL, we can combine signals and the HTML data type in order to give us a description of user interfaces. So our kind of first iteration of what a user interface might look like might be a signal of HTML elements. So a signal of descriptions of HTML elements using this DSL. So the idea is that the DOM is changing over time, and we want our signal to represent that. Every time the signal changes, we want to take the diffs and use virtual DOM to stick them onto the screen. And this is, I think, very close to what Elm HTML does. And I'm going to sort of work in steps from here and try to show how we get to the signal function model. So yeah, see Elm HTML for an implementation of kind of this style. So the first question is, how do we take that model and build in some concept of responding to user events? So that's great if I have some description of the DOM and it doesn't sort of interact with the world in any way except for sort of external things. So maybe there's a timer, and the timer, I just want to display a clock or something. That we can capture that with this already. But as soon as we want the user to click on a button, we need a way to be able to feed that button click back into the signal, so that acts as additional external input that we want to sort of feed into our system. And we can't represent that in the first model. So the first step is to just add a type argument. So we're going to create a type that represents all the inputs that we want to be able to all the inputs we want the user to be able to sort of initiate from the UI. We're going to put that in this type argument called input. So a UI with that particular type of input is a signal of HTML documents that contain these inputs in some sense. So we're going to parameterize the HTML type by some type argument of inputs. So for example, we might pick this singleton data type where inputs is just the only valid constructor is a button, just represents a button click. And then we're going to augment our DSL with these various event handler attributes. So on a click, I'm going to take the event, which in this case I don't particularly care about the contents of the event. And I'm going to return that input, button click. And that gives me a HTML DSL object with this particular type of input to the type argument. So UIs embed functions which construct inputs from DOM events to the input. So we're sort of taking the whole world of DOM events, which is sort of way too large. We don't want to sort of like our signal function to have to comprehend like the sort of DOM event type. So we take a function, we narrow it down to only the things that we actually care about handling, which in this case is button clicks. So we want those inputs, like I say, we want to be able to take those inputs that we got from the DOM, so that button clicked constructor, and feed it back into our signal. We want those to be visible as signals. So we want this kind of like future oracle of this signal of inputs to tell us what the future is going to look like with button clicks that haven't happened yet. So if we can see into the future, we can use combinators to build this future into our final signal that we're going to pass to virtual DOM. So on function, we might just use functions to represent it. So if we can describe our UI as a function from this sort of future signal of input to a signal of HTML descriptions using our DSL. So I should have called this stateful. I use the Elm the element in full P. But the way I described it earlier was the stateful function. So here I want to take these future button clicks and said stateful or full P is going to give us this step function behavior. So the step function is going to begin at 0, and on every button click I'm going to call the update function. And the update function is just going to increment this number. And I'm going to sort of accumulate the inputs I'm going to consider the future button clicks. And then once I have that signal, so this thing has a type signal of number, because our state type is number. I want to use the functor type class instance to map a function from numbers to HTML elements. That's going to take that number and just show it in a button essentially. And the buttons on click handler, here is where we tie the knot. This is where we're going to generate the inputs that get fed back into this kind of future signal. So there's something kind of odd going on here. This sort of relies on this sort of magic function at the top level that's going to be able to take something of this type and kind of tie the knot and feed these events back into this future signal. And that's kind of the motivation for signal functions. Is this all making sense so far? Any questions? Okay. So our UI type, the sort of second iteration, or third iteration, I guess, has become, sorry, the mistake, there should be an input type there. So a UI of input, of a particular input type, is a function from this sort of future event signal to our signal of time-varying DOM descriptions. As I said, this motivates the move from signals to signal functions. So signal functions can be thought of as black boxes or machines that take values coming out of one signal and produce values that you could use as the input to another, that you could treat as a source of other time-varying values, another signal. So conceptually, and again, this isn't the implementation in Halogen, we want to think of signal functions as functions. So a signal function of two type arguments has inputs and outputs. And we want to think of signal functions from I to O. There's functions from I'm sorry, this should be signal I to signal O. Just like here, sorry about this. Things that look like this, basically. So in that case, iteration 4 looks like, our UI type looks like signal functions, so black boxes that take inputs that haven't happened yet, and we're going to turn them into HTML descriptions that have the same input type, so that we can take those and feed them back into the loop. So in reality, I give a kind of incorrect conceptual model. The real implementation of signal functions looks more like this. So we have our input type and we have our output type. And a signal function from the input type to the output type looks like a function that will take the next input. So in this case, this is going to be our button clicked input, and it's going to return a record. So it's going to give us an output, which in our case we said that was going to be a HTML DSL object, and it's going to give us the next signal function. So we have this black box, and to keep sort of things pure, we're going to model state by so you have this machine that takes an input, and when it gets an input, it says, okay, here's the HTML you need to render, and here's a new machine that you can use to continue the computation with. So we have a machine that sort of spits out the next machine, and then you sort of discard that one and carry on with the new machine. Okay, so this is isomorphic to in Pascal GADT notation, this type. So just to give a kind of, this may seem a little opaque, so to give a kind of alternative motivation for this type, this is isomorphic to this type, where we can construct a signal function if we have some state type S from an initial state S and a function which takes the state we started with and an input to an output which is our HTML, and instead of giving me a new machine, I just give you a new state. So now you can think of this black box as really keeping an internal state that is going to change for every input. So you're going to run this machine by starting with the initial state, feeding in values of type I, and observing the outputs that come out, which are going to be HTML elements. And inside this box, we're going to have this state that keeps changing, and that constructs a signal function from I as well. Yeah. Okay, so here's the kind of the picture model that I'm going to use for the next few slides to kind of describe the ways in which we compose these things. So think of a signal function from I to O as this black or blue in this case box from which takes i's on the left and spits out o's on the right. So in Halogen, those are going to be our inputs that are fixed by the UI code. And then this is going to be HTML for the same I. So we can take inputs and spit out HTML documents. And inside we have this hidden S piece that's going to represent the bits of state that that particular part of our application cares about. So it might be a counter, or it might be just a little piece of the application state that corresponds to a bit of the DOM. Okay, so let's go through the type classes in this notation. So if I take, so functor says if you give me a function and signal from I to A, then I can map on the right that A, I can take the A to B function and map it over the A component and get a signal from I's to B. So in this case, I'm only changing what happens on the right-hand side. So I take that signal function and I need to construct a new black box. So I put the old machine inside the new machine, and every time that emits a value, I just glue this function onto the end so that instead of getting A's out, the only observable thing that happens is I get the A. And the description of this is we want to map up the output. So nothing changes on the input side. Functor gives us a way to change what happens on the output side. So when I had that counter and I was mapping over, mapping that function that created the DOM, we might do the same thing here. We might have a signal function that keeps its own internal state, responds to inputs and returns, sort of yields numbers, and I want to map the function over that to turn that into a signal function that takes inputs and yields DOM elements. Okay, so then applicative looks like this. So applicative says we can lift functions of 2 arguments over a type constructor. So if I have an SF, and again we're just going to restrict to the second component, is A. If I have a signal function from I to A, so a machine that takes I's gives you A's, and a machine that takes I's and gives you B's, and they each have their own hidden state type, S1 and S2, then I can create something which, given an I, the same I as both of these, it feeds it into both of them in parallel. This one's going to give me an A, this one's going to give me a B. And I'm going to take that function of 2 arguments, A to B to C, combine those two and yield a C. So this machine has 2 small machines hidden inside it. And the quote for this one is, we want to combine the outputs using a function of 2 arguments. Does this all make sense so far? Cool. All right, so far we've only dealt with the right-hand side. So now we want to think about things on the left too. So Profunctor is a type class that looks a lot like functor, except for that we can not only map on the right-hand side, we can map on the left too. So we have 2 type arguments. The second one is going to be a functor in the regular sense. We can map things over there. The left argument is going to be a contravariant functor. So notice this looks a lot like 2 functors glued together. But in the case of the first argument, in the case of the second argument, I have a function from O to B, and I change from a signal outputting O's to a signal outputting B's. In the left-hand case, I'm changing in the other direction, going from I's to A's instead of from A's to I's. So the left-hand side of the profunctor has to work sort of backwards, it has to map the function in reverse, and the right-hand side has to map it forwards. So that looks a lot like regular functions, right? Functions, the PureScript function type is an instance of Profunctor. So the domain of a function is covariant, and the codomain is covariant. So you get the same behavior. But the pictorial representation is, we have this machine from I's to O's inside. And on the right, when we get an output, we just want to apply this function so that you don't see the whole O, you just see the B, that's the result of it. And on the left-hand side, we take F, and instead of feeding an I to the machine, we feed the result of applying this F on the actual input, which is the type A. So where functor was map up the output, Profunctor is giving us the ability to map up the input and the output. Okay, so the next one is strong, and this looks a little bit like applicative, in the sense that we have 2 machines and we're sort of tupling things up. So in this case, we have this operator triple star, which takes, so the picture is a lot nicer than the type signature. It says if we can take input 1 to output 1 and input 2 to output 2, then I can take pairs of inputs of input 1, input 2, and the machine will spit out tuples of output 1 and output 2. So operationally, we take the tuple, split it into the two parts. We feed the first part to the first machine, the second part to the second machine, and we get an O1 and an O2 and the tuple back, and that's what the machine yields.
So I want to go.
Yeah, so we break up this tuple.
The whole tuple doesn't go to each.
No, sorry, yeah, I should have probably made that a bit more straightforward. Yeah, so the first part is we G-tuple, take the two components, feed the corresponding piece to the corresponding machine. Yep.
So a possible example of something like this would be you take mouse position over time as a signal, and you get out the result of a velocity in each direction of the y velocity and the next velocity kind of thing, right? So you say, how fast am I moving in each direction? Where you say, compute the velocity of the y and then compute the velocity of the x. And
yeah, so
we combine it back into a tuple that represents the velocity of each kind of thing.
Yeah, so there's various ways to describe this type class. Another way is to say, I'm just going to keep the I2 and just sort of feed it through and don't do anything with it, and this is going to take I1, I2 to O1, I2. So you can think about it in different ways. Like the way I like to think about it is sort of running two machines in parallel. So yeah, if you have two values you want to compute, and you have two inputs that determine them, then the kind of interesting thing about this though, and like you see this on the applicative slide as well, is that these hidden states are kind of like being composed. Right? So I went from S1 and S2. In order to keep the right amount of state around, you need to use the tuple of S1 and S2 in the full machine. So you kind of get this the sort of implicit state that's hidden inside these things. It grows with the sort of implications of these functions. So you sort of like implicitly slowly building up your application state. Yeah.
Is this type class parameterized so that I can use a different combining function?
So no, it's described in the library using tuple. But in practice, if you have functor or category or profunctor, I mean, this has profunctor as a superclass. You can use tuples in the map. So it's easy to write combinators using this type class that use other things. Is there another question? Yeah.
Well, I was wondering if that's the symbol and arrow, or is that related?
Which one, sir?
In the arrow type class, is that this the same?
Yes, I think, yeah. So I think it is the same one. In PureScript, arrow actually subclasses a bunch of these things. Yeah. Yeah.
So the only difference between like the signal data type and just functions in general is this like state that's being weaved in?
Yeah. So you can think of signal function as just a regular old function that happens to have some state inside that changes as it gets different inputs, but it's modeled in a pure way. Yeah. And then there's a dual to strong, which is called choice. And instead of taking tuples on the input, you now take sums. So if I take an either on the left and I get out an either. So if I got a left, then I run it through the left machine and I get a left. If I got a right, I run it through the right machine and I got a right. And again, we're tupling up states, we're building up this more and more complex state inside. And the motto for this one is we want to branch based on the input. Decide which machine to go to based on the input. Okay, so the next one is category. Categories, so the sort of canonical example of a category is the function type, and I said that functions look like stateful function arrows. So you expect these to be able to sort of glue these things end to end. If I can have a signal from A to B, signal function from A to B, and a signal function from B to C, I should be able to take the output of type B from the first one, pass it into the second signal function as input, and I'll get a C out the other end. And I can hide those two machines inside this single, more complicated machine. And we'll call this composition. And the other element of a category is the identity arrow. So the identity just says that you can take inputs and return something of the same type for any type A. And this looks like this very simple machine, but we don't keep any internal state, we just pass the value straight through, then changing it all. So this allows us to get access to the current states of the current inputs of the machine. In practice, you tend to use id, or it's actually aliased as input in the library to get a reference, to get the value of the input that sort of like cause something to happen. We had the stateful function for signals. We still have stateful functions for time. We still have stateful functions for stateful signal functions. The type looks very similar. Before we had a function from signal I to signal S, and we said that we want to think of those type of things as signal functions, so we just replace that chunk with SF. So we take an initial state, we take a function from states to inputs to new states, and we get a signal function out. And that you can think of this as sort of really capturing this idea of there's a state inside this thing. So if you can just explicitly describe one of these things in terms of states, then you can build one of these machines. And there's one more combinator that we use for building components. It's called merge. So this looks a little bit like a hybrid of choice and strong. It says that if I can get something I can branch on, so either I1 or I2, one of two types of input, I want to be able to get, so I have two machines. The first one takes input 1 to output 1, the second one takes input 2 to output 2. I want to get the latest value of each of those two machines in the output. So if I got the left, I'm going to get a new left component from the first machine. I'm going to keep the last value of the right component. So I don't have to force any data through that right component. It has its internal state, and I can determine the last value from that state. And similarly, if I get a right, you feed the right through here, get a second component, but I'm going to keep the last state from the left component, give the tuple back. So this is really useful when you have different DOM components on the screen and they don't tend to interact very much, and you just want to sort of paste them side by side. And you have two input types, one for each, and you want to get two DOM elements out and combine them into a bigger DOM element. Okay, so that's like a nice way of thinking about a lot of these type classes, just pictorially. But the reason this is interesting is that it allows us to build signal function graphs. Sort of building these signal function graphs explicitly using these combinators. So we might describe our application as this large flow from some top-level input, and maybe we branch based on an either, or just some function that determines one of the two branches. And then in the left branch, we map over a functor. In the right branch, we do some profunctor stuff. And you can have all sorts of stuff in here, and you just build up this bigger and bigger description of your application using signal functions. And at the top level, we're going to take this signal function and pass it to a function that knows how to do this tying the knot, taking the inputs and feeding them back into the signal function. And each one of these the nice thing about this as well is that each little box has its own little piece of state. So it's kind of a little bit like, think about actors, right? Actors have state, and you feed them inputs and they yield output to other actors. Everything's just kind of like nice and it's stateful, but each piece of state is encapsulated in one of these little boxes. Okay, so we said UIs. We want to talk about combining these things into components. UIs are constructed from signal functions, the HTML DSL, and every part of it was just described using pure functions and data. And that makes it really easy to bundle functionality. Let's say we want to take a component and make it reusable, or we want to write some mix-in functionality. It makes it really easy to bundle functionality into components or reusable pieces using higher order functions. Because everything's stateless. State is modeled using pure functions, so you don't have to worry about the typical problems of using, when we're building components, we don't have to worry about state essentially. So a pure component is given by, so we have three type arguments. We have n, which is a monad, inputs and outputs, and it's going to be a signal function, so it's black box that takes inputs to HTML descriptions. And before we were embedding events and inputs in here, now I'm going to embed monadic computations of outputs. So in practice, this is going to be the ath monad that John was talking about, which basically allows us to retrieve our inputs, the next input, using things like ajax. And to render a component, we have to have these two types match up. So we've got I, instead of O, this has to be the same I. And then we pass it to this thing, run UI, which takes a component with those two types matching, and ties the knot, passing the inputs in when they happen, using virtual DOM to render things to the DOM. And that all gets just bundled up as something in F, which you can embed in main. Okay, so I said pure functions make it easy to build components. There's also a bunch of mixins in just a few in the Halogen library. It's also easy to write Mixins because you're just sort of dealing with higher order functions to combine functionality. So the three examples I have, we have undo redo, which is a generic Mixin, so you can take any one of these black boxes and you can just augment it with an undo redo functionality automatically. Basically what happens there, I'll actually show this on a slide, but we replace the state type with a state type that captures future and past. You can have a Mixin that does hash-based routing really easily, and things like breadcrumbs and sitemap functionality. So you can build these generically on top of any state type. So here's an example of undo redo. So we had this state type S that was inside our black box. We want to change that into a new component which uses this undo redo state of S. And the way this is implemented, we have a past which is represented by a stack, starting with the most recent past, going backwards in time. We have a present, which is a state, and we have a future of things that have been undone that I could potentially redo, starting with the sort of most recently undone. And this is like a list template, right? So you have this idea of a focus, which is the present. You can move along the list by using undo and redo. And then once we've modified the state type, any invocation of the stateful function, which had this type S to I to S, we can take a function from S to I to S and turn it into the corresponding function type, but with all the S's replaced by the new state type. And this basically gives us the function we have to pass to stateful for free.
So because you're keeping state in each of these signals, when you do an undo, are you undoing on a single signal, or can you do it on entire trees?
So both. You can do it on an individual box, or you can, given that these things compose just into bigger boxes, the whole application at the top level is just a giant box. So you could apply this there, but the problem then is, chances are somewhere in that giant box is going to be some ajax happening, and like you're not just modifying the state type, there's sort of implicit modification of the data space happening, and that, then you're going to run into a situation where things don't.
Yeah, so I was like, oh,
Yeah.
because you can't really locally undo. It's like
So in practice, it's all about sort of factoring where the effects happen, right? So you want to describe sort of pure components with no effects and use undo on those, and then use things like functor to build that up, or functor, and there's something called hoist component which just lets you interpret like the monad in path, so that you can sort of you can use undo redo on a pure component and then lift it up into AF in the right way, stuff like that. But yeah, you're right. So we can modify any signal which uses stateful construction to add an undo redo for free. And then there's a bunch of, so this is all nice, and this works really nicely if you don't have to deal with these problems. And then there's this kind of awkward squad of 4 issues that in real world applications you have to deal with. I'll just quickly go through how we deal with these. And some of these are actually kind of still open problems for us, so you might have ideas and discuss these things. The first one is ajax. So this is actually the simplest one to solve. I said we parameterize the output by this type, this monad m. In practice, at the top level, m is going to be the AF monad. So we choose m to be AF, and then instead of directly returning the value to the signal function, we return an asynchronous computation that at some point in the future is going to return an input that we pass into the signal function. And in practice, that's going to be implemented using things like ajax. In practice, m at the top level is the AF monad. And just brief mention, this has sort of a nice side effect that since we've parameterized m in the component type, we don't use the AF type directly in the definition of component. It's actually polymorphic, so that means you can choose m to be something else. You can choose it to be identity monad, which means that that particular chunk of your application doesn't have any monadic effects when it generates inputs, or you could choose it to be F, which means that everything it generates is generated synchronously, or you can keep it polymorphic, which means I don't have any effects, but I can still fit into other components that do need effects, or you could use a free monad, so you could use something like this for mocking things like ajax requests. So instead of using AF, I'm going to use this mock monad. The one is free. This monad constructed with the free monad on this mock signature. So mock says, I want my monad to look like something which provides the ability to take a request and return a response. And then I use free to turn that into this kind of minimal monad that implements that signature. And then I write my component in that monad. And then for production, I use this combinator called hoist component that it allows us to map the natural transformation over the monad that we use. So if I want to use it for production, I interpret it in the auth monad. If I want to use it for testing, I might implement it using identity or f or some other monad that doesn't go to the database or do ajax or what have you. The second member of the awkward squad is how do we deal with external input. So far, all of the input that we fed back into the signal function, in fact, all of the input that the signal function sees comes from some future click or mouse movements or something like that, click or input change or something from the DOM. But we also want to deal with things like mouse movement, timer ticks, hash change events. And the way that we deal with those is we have this concept of a driver function. This is sort of very low level and ugly, but essentially gives us a way to just feed the machine with inputs that didn't come from inside the machine. So the run UI function that I showed earlier that does this tying the knots with inputs, as a side effect, it hooks up the inputs that are generated to the start of the signal function, but it also provides you this driver function which allows you to sort of just inject additional inputs into the machine. And this allows main. So in main, we're going to set up something like a mouse listen event that drives the machine in addition to any DOM element events. So the nice thing about this, it is ugly, but the nice thing is we've successfully separated all of the kind of external events. We have sort of an entirely pure description of what a particular fragment of our application looks like, and then everything effectful has been pushed to the boundary of the application right into main. So we've kind of extracted the sort of largest nice component of our application, if you like. And here's a quick example. So run UI, in practice, you pass it this UI object that bundles a signal function. You get a node out and a driver function. You append the nodes and body of the document, and then maybe I set up an interval on the second long tick, and every time I get a tick, I call that driver function with this tick input, just sort of feeding the machine every second. So another member of the awkward squad is third-party code. The signal function model works really nicely when you're dealing with these pure components, and we ran into some issues in Slam data where we wanted to be able to use off-the-shelf components like ACE, the editor ACE, and then the problem is the whole JavaScript world doesn't sort of like buy into this nice pure model, right? Like in practice, things are modeled using imperative APIs, and we need to be able to fit that in somehow. So the current solution, which I'm not particularly happy with, that needs revising, is we basically annotate. We use data attributes to attach state to particular divs or elements, and then we provide a hook that allows the developer to go in after every render, after every time the signal function is hit. We provide a hook so that the developer can go in and make sure that the data attributes got synced with the ACE component or whatever third-party component is being used. So not particularly pleasant, but there's an idea for ways in which we could improve this. One idea was to have to basically allow widgets and components to define their own type to query DSL. So in the case of the ACE editor, you might want to have a query language that said things like clear the buffer, and that has a return type of unit. So we're typing the query with the return type of unit, and give me the current value of the buffer, so that would have a return type of string. And then instead of using the auth monad, we use the free monad transformer to basically embed this query language inside the computations that produce events. So instead of just producing an event directly, I could say things like, give me the current value of the buffer, if such a condition holds, clear it, and then yield this input. And like I said, widgets, components interpret their own DSL, so they fix their type to query DSL. And in practice, the way this would operate is that just as those hidden states inside components compose up to, we tuple up the state, building these bigger and bigger states, we'd also kind of compose the query DSLs as the components got combined. So that at the top level you have this gigantic hopefully not too gigantic, but large DSL that represents the queries that can happen across the entire application, all the widgets in the application. So this is nice because it allows us to avoid re-rendering things. It turns out the data attributes approach means that you have to re-render a few too many times. And you can avoid things like bulky updates to the DOM. And then the last thing is I want to be able to provide additional backends. So the signal function machinery, we spoke about having this as a toolkit rather than framework. Signal function machinery should be reusable, and we should be able to apply it to other types of application, like Canvas applications, SVG applications, WebGL applications. Maybe we want to use picking in WebGL to try and find inputs to pass into the signal function, or on-click events in SVG. So the way this is implemented is we basically just back to run UI into two pieces. We have this concept of a process, and a process looks like a signal function that yields effectful operations. So every time the signal function runs, it spits out a new effectful operation and we run it in main. Or main loop, sorry. So main loop is this function that takes a process and turns it into something we can embed in main of type F. And then we have another function which takes those signal function components using virtual DOM and turns them into a process. But the nice thing is now we can define processes for applications that can be interpreted in ways other than using virtual DOM, using main loop. And that's it. I was going to give a quick demo. I don't know what time's like, so I'll just probably ask for questions and get some lunch. Is lunch ready, John? Yeah. Okay, well I can give a quick demo if people want to see it.
Yeah.
All right, cool. All right, so I put together this. Actually, get a demo of the pulp build tool as well. So I just built this just before the talk. So I use the pulp build tool to initialize the project. So you type pulp init, and it's going to initialize a bower.json file for you, a source directory and a test directory. So in pulp, source contains all your library source code and application source code, and test contains your test suite. And then you can say things like pulp build.
Is pulp an alternative to Yo?
Pulp is, yeah, so it bundles the same functionality that you get from Bower and something like Grunt, Gulp, Yeoman. It basically is kind of like, it's an attempt to make like one tool for PureScript development. It's really excellent actually. If you just want to get started with PureScript, like I'm going to start recommending using Pulp in the book. I'd definitely recommend giving it a look. Okay, so I said Pulp build, and it said building a project and build was successful. You can say Pulp test, and I don't think I have any tests, so it will say you should add some tests. You can say Pulp browserify. So if you're familiar with the JS ecosystem, browserify, I don't know. Is a way of taking common JS modules, which is something that PSC Make will build, and turning them into a bundle that you can stick in the browser for deployment. So if I run that, it'll build the project, and then when the build is done, it'll say it's browserifying everything, and then I'll end up with a single JS bundle with all my PureScript modules in it. And this is the kind of Hello World application that I've built. So it's a single box of state, and it contains a boolean and renders a button, and when you click the button, the boolean gets toggled. It's crashed or something? It's going on. Okay, there we go. Yeah, so it just looks like this. You toggle on and off, and I'll show you the code for that. Okay, so we have quite a few imports. Standard PureScript stuff, core libraries. This is the simple DOM library that I'm going to use to be able to attach the node that virtual DOM gives me and stick it into the DOM. Some Halogen Applicative modules. So I use Halogen, which gives me this top level time not functionality, a main loop function. I have signals, which is all the signal function stuff. I have a component, which is kind of like bundles up the signal function code into component. It's component abstraction. And then some qualified input. So I have the HTML DSL here. So I'm going to take the HTML DSL using the H namespace. and the attributes and events in the A namespace. Okay, so this is going to be a function implemented using simple DOM that's just going to append the DOM to the body. So that's sort of like not Halogen related, but is needed. And then here's where we're going to describe this state machine. So our state machine has a state type. I'm defining it as a new type around a record just so I can give a label to this boolean. And it's just one boolean which I'm going to call on. So is the machine turned on? And then the only inputs I care about are the ability to, I want an input that says toggle the state inside the machine. And then this type of so it's a little complicated, but you can kind of ignore the applicative bit. Basically, it just says this component deals with inputs and responds with new inputs when events happen. And I don't care what monad you want to use in other components for handling things like ajax, because I don't need them. I can just kind of unify it with whatever monad you pick. And then the implementation of this box is using stateful. So stateful took an initial state, so we start with the state that in which the machine is off. And then it takes a function which responds to inputs and takes the original state, gives a new state, and that's this update function. And then this is similar to the example I gave before, where this gives us a machine which yields states. I want to take all that state and turn it into a DOM representation. So I use a functor, use this map function operator to apply the render function to the result of this signal function. Every time I get a state, I'm going to return a DOM description, and the DOM description is going to just be a single button. The attributes are going to be the onClick event handler. It's going to yield this toggle state event on every click, and the content of the button is going to be a text element. If the machine's on, then I say on, and if it's not, then I say off. And the update function takes a state and input gives a new state. And whatever the state was before, when I say toggle state, I'm just going to return a state in which if it was on before, then it's not now. I'm just going to use the not function to negate that. The main function, I use run UI. So I have this component that describes a loop for inputs to inputs, and I need to tie the not. Run UI ties the not and gives me the initial node that can append to the DOM. And then from then on, this is kind of like the same concept as in Ath, we had this idea of forking. Run UI essentially forks off this this thread, if you like, that's going to take the signal function and keep iterating and patching the DOM with the virtual DOM phase. And that's it. So that's kind of Hello World in Halogen. And then I have a few other examples. So the examples directory in Halogen has a few things. So we have these kind of deal with the standard case, and then a couple of these like awkward squad cases. So counter is this idea of like feeding the machine with external inputs. So this is what counter looks like. It's just the state is a number, and we're feeding the machine with inputs to increment the counter. But we don't have any buttons or inputs or anything here, so there's no inputs coming from inside the machine. These are all external. The Ajax example shows this how the solution for how we deal with monadic inputs. So this, if you've seen the try PureScript web service, it's it's got an open endpoint. You can just calls enabled and things. So you can just you can call it from your own application. So this basically implements try PureScript as a Halogen application. So you can press compile, and if you look, so this compiles, it runs try PureScript and gives you all the JavaScript. If you actually watch what happens here when I press compile, it'll say working. So there, what we're actually doing is we're using a particular choice of monad. It uses ath to actually, instead of yielding one input, it yields two inputs. So it yields the working message, which updates the DOM and just patches in that working message, and then it's going to fire off the Ajax computation. When it comes back, it'll fire the input that sends the JS back into the machine that came back from try PureScript. And this is kind of related to that A-stream thing that John was talking about. We have in practice the monad we use is not actually ath. It looks like list T of ath. So you can actually yield multiple inputs when you're doing Ajax call, so you can do things like sending progress updates to the browser or for a WebSocket or something like that. To do, this is another example of kind of the simple case, the pure case. It's just to do MVC type thing. And this has an example of the undo redo functionality. So you can say hello world, walk the dog. And then you can mark these as completed, and you can undo in step, or you can redo. And like I said, this comes free from that undo redo mixin. So it looks like this is So this is the code for to do. So you see we have this input type. We have various inputs that we want the state machine to be able to handle, like request to add a new task, update the description on a task, mark the task as completed, remove the task, and then the last two are undo and redo. So to be able to support undo and redo, our input type has to be a sum of an undo, a redo, and something else, and that's captured by this support undo redo type class. So it basically looks a little bit like Prism, where you kind of want to say map in one direction to get the undo redo out, and then in the other direction it might not be one of those components. So we can fail with a maybe. So we have just in the case of undo redo, nothing otherwise. But then if you remember the type signature of that undo redo function, with undo redo, that was the thing that allowed us to take our update function that we passed to stateful and turn it into this augmented augmented update function that uses this new state type. So again, I'm still using stateful, but I'm using this new state type and this modified update function. And the update function doesn't have to change. It's the same one, but it doesn't do ajax or anything, so we don't have to worry about this synchronizing state problem. That's it, I think. Oh, there's the ace one, but yeah. Last example. Oops. So this is an example of integrating with the ace editor, which is that problem of integrating with third-party components with pure components. So third-party components can still yield events back to the signal function. So I just press Control-C, and I got an input generated from the ace component that said some text was copied, and I can render that into the pure fragment of my UI. And you can also send sort of requests to the ace component. So if I want to clear the text, this is implemented using that data attribute trait, where I essentially have a gigantic data attribute that has all the text in the ace component. And then on the post-render hook, we're going to synchronize that data attribute with the ace component using its own imperative API. So yeah, that's it. Any questions? Anything? Like, dig into the code more or whatever.